Hello, welcome to the Fairbanks Museum and Planetarium Earth Science Lab here. I'm Michael Simoniello, and today we're going to do just two quick demonstrations of one of the phenomena that is always occurring around us here on Earth. It has to do with heat. We're going to be talking about convection today. And in order to show you guys how convection works, we're going to be doing two quick experiments, but before we get to that, we're going to have a quick discussion about exactly what convection is. So if you've ever heard the common sense phrase that heat rises, you already understand half of what we're going to talk about, convection. But if we want to get into the scientific language of convection, we have to start with a difficult word that you may not have heard before, thermodynamics. Thermodynamics, if you break it down into the two words that make it up, thermo, like thermos, and dynamic, which means movement, that word thermodynamic literally just means the movement of heat, or how heat moves. So thermodynamics is the study of how heat moves and changes all around us in our daily lives. Convection is one type of thermodynamic phenomena, and in order to really understand convection, we have to think about the two first laws of thermodynamics. So in all of physics, physics being everything that happens on Earth, everything that happens is governed by the laws of physics. Thermodynamics is a part of the physics of our Earth, and so it has laws that go along with it. These laws are basically rules that physics has to follow. You'll never find any of these laws being broken anywhere on Earth, so you can rely on them whenever you're studying any kind of physics, whether it's gravity or colliding objects or the movement of heat, which is what we're doing right now. So the first law of thermodynamics that we're talking about is this guy right here. And the first law states that heat is a form of energy. If you saw my class about energy, this might be familiar to you. But this basically means that, as any other form of energy, heat can't be created or destroyed. So all of the heat that's in the universe right now is never going to necessarily go away, and there's never going to be any more than the total amount of energy that's in the universe today. But what this also means about heat is that it can be converted from one form of energy to another. So heat energy could be transferred to mechanical energy or radiation energy. So this heat that we're going to be talking about today can change forms, but you can't create or destroy it. And that's really the key to what we're going to be thinking about today. We're going to be changing the energy of this pot of water here. And we're going to be moving our heat without adding or destroying any heat energy. The second law of thermodynamics here is one that we're all familiar with just in our day-to-day actions, but might be a little bit confusing to explain. And the idea is that heat energy always moves from warm bodies to cold bodies. All right? And the reason that this is true is because, like all forms of energy, heat is always looking to find a state of equilibrium. That might not be a word that you've ever heard before, but think about the word equal. The word equal is in equilibrium, and equilibrium basically means that the energy wants to even itself out. So, as an example of finding equilibrium with heat, something that we're familiar with, if you have a cooler filled with ice, and you have a warm can of soda, and you put that can of soda into a cooler of ice, and you seal the cooler, and you fall asleep, and you come back to the cooler tomorrow, 12 hours later, and open it up, you know that what you'll find is a cold soda, right? A soda that's been cooled down, and probably a bit of melted ice. So that's common sense. That's something that we know will happen if you put a warm soda into a cold cooler. But what's really happening there is this second law of thermodynamics. The heat from that warm soda that heat energy is literally moving out of the soda and into the cold ice, and it's melting that ice. So what the whole system, and here the system is everything inside of the cooler, so the ice and the soda. The ice and the soda are trying to equalize their heat energy. And because the soda is warm and the ice is cold, the soda is going to cool down so that its temperature gets closer to the temperature of the ice. And the ice is going to warm up a little, so its temperature is going to get closer to the temperature of the soda. And then when you open up the cooler, that soda is going to be the same temperature as the ice around it. A little bit of the ice will be melted, probably. So that's an example of energy trying to find equilibrium. And so now, convection is an example of this equilibrium that happens in the air all around us, in the Earth's atmosphere, and that also happens in any body of water. If you've ever boiled water on the stove or poured cold milk into hot coffee in the morning, you've seen convection happen. So, again, we come back to this common sense idea that you all know: heat rises, right? In a building, you'll probably know that the second floor of your house is pretty much always warmer than the first floor of your house, because any heat that comes out of your furnace or your wood stove on the first floor of your house is going to want to travel to the second floor. Why does this happen? It's kind of a confusing question, right? Anybody can tell you that heat rises, but if you ask them, well, why does heat rise, they might have trouble explaining that to you. So the scientific reason why heat rises is that the actual particles of air, the air molecules, those very, very, very small particles that you can't see with your naked eye. Think about individual water molecules in this glass of water here. There are billions and billions of individual water molecules inside of this glass here. In the room that I'm in right now, there's hundreds of trillions of air particles. And as those particles heat up, their energy increases, right? So again, heat is a form of energy, and you guys might know, especially if you saw my class on energy, when particles get energized, whether it's energized by heat, whether they're getting hotter, or whether they're being charged with electricity or something like that, those particles will start to move faster. All of the little molecules, the little water molecules inside of this glass here, are vibrating very slowly, and they're moving around inside of this glass. In a moment, when I use this torch to heat up the water, those water molecules are going to start moving faster and faster, and eventually, if you've boiled water on the stove, you've seen what happens when you energize those water molecules to about 212 degrees Fahrenheit. They start to move so fast and they get so energized, they split apart from one another and they become water vapor, right? Steam. And that steam is so light compared to the water around it that it floats up to the surface of the water and comes out as steam, water vapor that we can see. That's what all of those bubbles are inside of any pot of boiling water. And so, as I heat up the water here, those particles start moving faster and faster, and they'll start to move away from one another. And as they move away from one another, hold on, sorry. As they start to move away from one another, that water starts to actually get lighter. And it's the same thing that happens in the air. If you heat up, if I started my torch right now and I started to heat up the air around my torch, the molecules would start to move faster, they would move away from one another, and that would make that air lighter. And this is a hard thing to understand because you can't see air, and it's hard to see water moving inside of glass. But as that air heats up and gets lighter, it's going to begin to float up. And the reason is because it's less dense and therefore lighter than the air around it. Okay, so let's start with this experiment here so that you can really see what I'm saying. It'll probably be easier once you can see it. So I have my tank of water here and a little bit of cold food coloring that I've been keeping in the fridge. Whoa, spillage. I'm going to put that food coloring right down into the bottom of the tank here. So you'll notice that all the food coloring is staying right at the bottom. And that's because the food coloring that I've been keeping in the fridge is colder than the rest of this tank of water here. And that means that the molecules of the food coloring are moving slower than the molecules in the water tank. And that means that they're moving closer together. That makes them heavier when they're closer together. It makes them denser, and that makes them sink. Okay. Okay, so you can see now that all of the food coloring has stayed to the bottom of my glass because that food coloring is colder than the water around it, so it wants to sink. But watch what happens as we heat up that food coloring very quickly with this torch here. The torch is pointing right at the bottom of our tank here. So it's going to warm the whole bottom area where that food coloring is. Pretty soon, you'll be able to see that food coloring start to rise. So I haven't moved this jar at all. The water is perfectly still. But all this food coloring is beginning to rise. Can you see that? That's because I'm heating it up. And as that food coloring water heats up, the molecules start to move faster and faster. And that food coloring water is actually lighter than the water around it. So it rises up to the surface. But now, if you look carefully at the food coloring that's near the top, and you watch those swirls, you'll start to see them swirling back down towards the bottom. Especially if I shut this off. So now the whole jar is pretty well mixed with food coloring. But if you look closely, you will be able to see the food coloring falling back down to the bottom. And if I leave it like this, eventually quite a bit of that food coloring will settle back down. The reason for that is that the hot food coloring rises to the top of the glass, but way up here, the water near the top is much cooler than the water down here because I was only applying heat to the bottom of this glass. So that hot food coloring rose to the top, but then once it got up here, it wasn't being heated anymore and it started to cool off. And so as it cools off, those water molecules lose energy, they start to get closer together and then become denser and heavier again. So then the food coloring water starts to settle back down to the bottom. And it will create a convection cycle where water at the bottom is heated up, brought to the top, cooled back down, brought back to the bottom where it's warmed up again. So that same water is going to be cycling and cycling. You could put the computer back for a second now. So this is a diagram of that exact cycle here. So this is true in water, but it's also true in our own atmosphere. This down here, that's our heat source. So in the case of our experiment, it was this torch, and that was a whole lot of heat all at once. But in the atmosphere, that heat source is actually the surface of the Earth. the surface of our Earth, whether it's soil or the ground or whether it's the ocean, it's constantly being warmed by radiation from the sun. The ground is the warmest part of the entire atmosphere. And so, the air that's closest to the ground or the water in our tank that was closest to our torch is going to get warmed up. As it heats up, that air or water is going to move up either inside of the tank or in our own atmosphere. And so now, as we just mentioned, the farther you get away from that heat source, the colder the air or water is, right? Think of our own atmosphere. Way up here at the top of our atmosphere, you're getting very close to outer space. And outer space is very, very cold. So, the surface of our Earth is very warm. The edge of our atmosphere is very cold. So any air that gets warmed near the surface of our Earth is going to travel upwards until it gets close to outer space, where it cools back down. And as it cools, those molecules come back together, get heavier, and then fall back down through the atmosphere until they get close enough to the Earth's surface again to heat back up. That's what we were seeing inside of our glass here, and that's what's happening all around us in the atmosphere. We just can't see it because we can't see the movement of air, but we can feel the movement of air. This cycle here is what creates a lot of the wind that we experience in our everyday lives. Wind, of course, is moving air, and particularly in this part of the cycle here, close to the ground, where cool air is being warmed up by the surface of the Earth again and then being sent back up into the atmosphere, those are the winds that we experience here on the ground. Okay, now let me think about what I'm going to do next. What I'm going to say next. You can leave that on. Don't leave that.
Yeah, no, just.
Can you plug it back in?
Dark.
Actually.
Yeah,
it got dark again. What else do I want to say before I do the next experiment?
Storms, do you work that in? Or the desert?
Yeah.
Like the valleys in the desert have very windy, more than other places because that convection is occurring quite a lot. The heat escapes. There's dry air. There's not a lot of clouds. The heat escapes.
Yeah. Yeah. That's why it's close to the equator. It's very dry. So they go to the Sahara Desert or the deserts in northern South America because those are the parts of the Earth that are getting direct heat. But then at the meridians, that's where all of that air rises and falls back down to. So those places are very moist because that's bringing all of that moisture back around. I don't really have time to talk about that kind of stuff. I want to keep this kind of short and sweet.
Michael, do you mind us sitting here watching?
No. Okay, now I know what I want to say. So going back to our... Hold on.
Do I move the pot out of the way?
No, I want the pot. That's what I'm trying to show. So going back to our glass now, we've taken the torch away for a while, and you can see that the food coloring is now everywhere inside of this glass. It's dyed the entire glass green, and this is really another example of equilibrium inside of our glass here. The originally cold food coloring has now mixed completely with the warm water, and now they're both the same temperature, and that's why the whole thing is green now. So the food coloring, which was cold, got warmed up by the surrounding water, and along with that, the surrounding water got cooled down slightly because of the cold food coloring. Now everything inside of this glass is the same temperature, and you can see that because of the food coloring. This is what's happening in any glass of water that you drink, and it's even happening in our oceans and in our atmosphere. Everything with heat energy, which is everything on our planet, is constantly trying to reach a state of equilibrium like this tank here. So the water at the top is now just as warm as the water all the way down in the bottom. But now it's time for us to do our second experiment. So, this is actually nice to be able to do cuts and stuff like that.
So cream in your coffee is an example. I thought you.
Well, that's what I'm going to be showing here. So going back to our diagram here for convection currents, this is what a convection current looks like from the side, like how we were looking at it from the side of our glass here, where we were heating the bottom and we watched the liquid rise. Now we're going to see this same process of convection, but from the top down. So you could imagine this now as if you are an astronaut in outer space looking back down on planet Earth. This is what our atmosphere would be looking like, except you wouldn't really be able to see it. The great thing that we can do here with liquid is, again, we can dye the actual water that we're using so that you can see those convection currents as they're happening. And I'm going to need your help again here. Sorry, Anna, am I taking up all of your time here?
Mm-hmm.
Do you want to unplug her so she can move that?
Oh, no, she can. So kind of tip it up so that you're looking straight down into the pan here.
Oh, like all the way up.
Yeah, like all the way up. Try to hold it steady there as best you can. That's perfect, Anna. Thank you. So, now here we have a pie plate which is filled with water and a little bit of soap, a little bit of detergent, just to give it a blue color. We're going to add, again, the green food coloring to it. But remember, this time, we're looking at convection from the top down. So you can think of this blue pie plate as if you're looking down to the atmosphere of the Earth. So you see how that food coloring pretty much totally disappeared? Because again, it sank down to the bottom of the pie plate. I'm going to turn on my torch again. And we're going to be heating up the center of the pie plate. And watch closely what happens with that green food coloring. Ah, perfect. So, can you see how this green food coloring is bleeding up to the surface? And if you look really closely, you can actually see the different convection cells. So the way that convection works is that there'll be one small area, the area directly above my torch, where the water is coming up from. And if you look here, it should be right in the center. You can actually see the green food coloring water billowing up from the bottom. If you have ever made coffee and poured cream, cold cream, into hot coffee, you can see these exact same kind of cells or swirls. Watch what happens now when I move my torch now over to this side of the tank. I can create another cell over here. Might take a moment. Aha. So right over there, hopefully now you can see that the food coloring is swirling over on this side of the pie plate instead of where we started, over on this side. So these... Okay, you could put that. These cells that we were just seeing from the top down now is what's responsible for some of the wind that we experience on our Earth, but it's also part of what creates things like thunderstorms. You guys might have heard that thunderstorms are created when a mass of cold air reaches a mass of hot air and they begin to mix together. That mixing is this convection, where the air will start to cycle around itself, the cold air mixing with the hot air, and that's what creates those massive thunderhead clouds that are very tall. They form inside of these cells, and that's what creates lightning. It's actually those water molecules, the ice molecules, and the liquid water molecules, the water vapor, rubbing all against one another to create static electricity. That's what causes lightning, which is super interesting. So, oh my gosh, why does the computer shut off as I'm recording?
It doesn't shut off, it's still recording.
Even when the screen goes black?
Yeah, as long as the green light is on.
Oh, that's okay. Okay, so let's do a quick final review of convection here. So convection is... Oh, hold on. I have to restart. I forgot what I was going to say. Oh my gosh. Okay, so let's quickly review convection here. Convection is the movement of heat energy in any body, particularly here in terms of the Earth. Convection is important in terms of our oceans and in terms of our atmosphere, these giant bodies of liquid water or gaseous air. And what drives convection is heat, the tendency of heat to find an equilibrium. All kinds of energy, whether it's electrical energy or heat energy or radiation energy or kinetic energy, they all want to equal themselves out. Heat energy does this by causing these convection currents to form. So convection uses these first two laws of thermodynamics. And we have to remember that this is the shape of these convection cells. They're cycles, right? Remember that heat can't be created or destroyed, but it is always moving around, basically, trying to reach equilibrium. As long as there is a source of heat and there is a difference of heat between the area near the heat source and the higher areas of the atmosphere or the ocean, these convection currents will continue, and the convection currents will keep going. They'll keep cycling the air in the atmosphere or the water in the oceans until all of that material reaches the exact same temperature. And I probably don't have to tell you that our Earth's atmosphere is never all going to reach the same temperature. And the Earth's oceans are all never going to reach the same temperature. Think of the fact that half of the Pacific Ocean might be exposed to the sun. It might be daytime on half of the Pacific Ocean and nighttime on the other half. So there's going to be a difference of temperature just because of where the sun is shining. So because of that, these convection currents are never going to stop. They're always happening in our atmosphere, and it's responsible for some of our weather and wind. And they're always happening in the ocean, which is responsible for some of the movement of our ocean waters. So hopefully this fast explanation and demonstration of convection has helped you to understand a little bit more about how our Earth works. Thank you very much for tuning in to my class today.